Welcome to This Explainer. Today, we're diving into something I like to call the sculpture method. Basically, we're going to take a massive, raw block of physics information, completely chip away all those bad study habits, and reveal a masterpiece understanding of Cambridge IGCSE freefall. So if you've ever felt completely overwhelmed by forces and motion, trust me, you're in exactly the right place. Okay, here's our game plan for today. We'll kick things off with a free fall challenge, move right into our 4 steps to mastery, learn exactly how to translate physics data, dodge those common exam traps, and then we'll wrap it all up with some essential memory prompts.
All right. Section 1, the free fall challenge, building the foundation.
So before we even touch a physics formula or even think about drawing a graph, let me ask you this. What physical effect, measurement, or prediction actually depends on understanding free fall? Really think about it for a second. I'm posing this challenge because we need to establish the real-world stakes right out of the gate. Because, let's be honest, if you don't know why a concept matters in the actual physical universe, just memorizing the math is not going to save you on exam day. And that brings us to a concept the source material calls application-first learning. The whole idea here is to completely break free from rote memorization. When you start by looking at how free fall is actually applied, the concept suddenly feels, well, necessary. It stops being just some decorative fact you have to memorize for a Cambridge 625 paper, and it becomes a vital tool, a tool you can use to reason your way through completely unfamiliar exam questions. Moving right along to Section 2, 4 Steps to Mastery, the Blueprint. Let's see how this application-first mindset actually builds our primary tool for exam success. This right here is your ultimate 4-step blueprint. And what's really cool about this is how it guides you from just recognizing a problem to firmly connecting it to a real-world experiment. First up, you identify the physical quantity or phenomenon. Second, you state the relationship. So this is where your symbolic rules or definitions step in. Third, you explain the underlying physics in plain, simple terms. And finally, fourth, you connect it to an observation, an experiment, or a real device. It's essentially a foolproof chain of logic. And why exactly do we rely on those 4 steps? Well, there's a great quote from the source text that really hits the nail on the head. The best answers show both understanding and application. You see, Cambridge IGCSE examiners, they aren't just looking for human calculators. No, they're specifically looking for students who can seamlessly blend theoretical, abstract knowledge with highly practical, real-world scenarios. Which brings us to Section 3, translating the physics, shaping the answer. This is where we grab our chisel and really refine our everyday language into strict, precise physics vocabulary. Think of a kinematics graph as a highly compressed language. It's never just a picture. The visual data translates directly into physical meaning for free-fall scenarios. Take the slope, for example. That's your acceleration, or rate of change. The area under the line, that translates directly to distance traveled or work done. The direction gives you your vector orientation, and the shape of the graph itself tells you if a change is uniform or non-uniform. You absolutely have to be able to translate these features on the fly. But hey, remember our golden rule? Application first. Freefall isn't just about dropping a ball in a vacuum chamber. The principles of freefall are heavily used in transport and safety systems, engineering and energy networks, medical tech, and of course, astronomy and orbits. When you walk into that exam room, you should be able to name at least one of these areas where predicting outcomes through freefall physics is absolutely vital. And this all boils down to one crucial principle: cause and effect. A master-level answer relies on cause and effect reasoning to prove exactly why an object behaves the way it does. Whether you're dealing with fields, forces, or particles, you have to connect them to a direct physical outcome. Never ever just list isolated scientific facts, hoping the examiner will somehow connect the dots for you. You have to be the one to draw the map. Okay, Section 4. Avoiding exam traps, the critical eye. Now we're going to polish up our exam technique by contrasting some common flaws with the ideal high-scoring structures. So let's contrast the really common weaknesses like writing naked formulas, quoting processes without links, and giving unjustified examples with what the source calls the safest method: definition, relationship, explanation, application. Notice how utilizing the safest method completely chips away the irrelevant mistakes that bleed marks. It essentially forces you to justify every single thing you write down. Let's actually break those traps down a bit more so you can actively avoid throwing raw, unlinked facts onto the exam page. Trap number 1, writing the correct formula without explaining the variables. Classic mistake. Trap 2, quoting a scientific process without linking it to a physical effect. And trap 3, giving an example but completely failing to show why it actually follows from the physics. Basically, if you catch yourself writing the word without in your head when reviewing your answers, you need to go back and add that missing link. Finally, Section 5, Essential Memory Prompts, the final masterpiece. Here are the 4 prompts that will guarantee your knowledge is totally secure. Whenever you sit down to study a microtopic, I want you to literally ask yourself these 4 revision prompts. 1. What is the core idea? 2. What changes physically? 3. What quantity or graph actually shows it? And 4. Where is it used in the real world? If you run every single concept through these 4 questions, you're ensuring that you've built a complete, beautifully sculpted understanding of the material, one that is fully ready for any short answer or structured question they throw at you. Which leaves me with a final, provocative challenge for you today. Can you answer those 4 memory prompts aloud right now for freefall? Can you prove to yourself that you are relying on cause and effect logic rather than just memorized wording? Seriously, don't wait until you're sitting in the exam room to find out. Test your newly refined physics mindset today. Thanks so much for joining me for this explainer, and keep questioning the physics of the world around you.